In the previous lecture, we had left off with introducing the log normal distribution and talking about within and between worker variability. Now we are going to talk about how to quantify this variability and also estimate various parameters of the log normal distribution. We are now going to start with quantifying variability in worker exposures. In order to describe a statistical distribution of workers' exposures, we need to understand two descriptors of such distributions, namely the geometric mean and the geometric standard deviation. So what are these? So if X sub I is a sample of n measured exposures obtained from a group of workers, and if we then obtain the log transformation of each of these xi, then we get the yi's, which are the log transformed values, and yi is the natural log of xi. And if xi are log normally distributed, then the y's are normally distributed. And we are going to take advantage of our knowledge of the normal distribution or the Gaussian distribution to understand the log normal distribution. So the geometric mean, mu sub g, can be calculated as shown in this formula, where you take the log transformation of each measurement xi, and you add up all the measurements, and then you divide by the number of measurements. So it's exactly like you would take an arithmetic mean, except that you are taking the arithmetic mean of the log transformed values. And so what you end up with is the log of this geometric mean. So if you can then exponentiate this term, you would get the geometric mean mu sub g. The geometric standard deviation, sigma of g, is defined in a very similar way. Here again, in the bottom of the page, you see the formula for it. So instead of taking the standard deviation of the axis, we take the standard deviation of the log transformed values. So you take each log transformed xi and subtract from it the mean of the log transformed value. So that's the natural log of mu g. And you square the difference, and you sum all these square differences, and then you divide by n minus 1, and then you take the square root of the whole thing. So this is the formula for standard deviation that we are all familiar with, except we are doing it on log transformed values. One interesting thing about log transformed standard deviation is that you can use the law of subtraction of logarithms. So each of these terms, log of xi minus log of mu g, can be expressed as log of xi divided by mu g. That's one of the laws of logarithms. So what you end up with is, in fact, a ratio of two concentrations, xi and the mu g is the geometric mean concentration. And then you take the square of it, you sum it, divide by n minus 1, and take the square root of it. So what you end up with is, in fact, a dimensionless quantity. And so the geometric standard deviation, which you can obtain by exponentiating this formula, is, in fact, a dimensionless quantity. Whereas the mu g above this, the geometric mean, is, in fact, in the same dimensions as concentration. If we are just looking at the log transformed values, yi, then as I showed in the previous slide, we can obtain its mean, which is just the log of the mu g, and that is the arithmetic mean of the log transformed values. And sigmas of y, which is the log of the geometric standard deviation, is just the regular standard deviation of the log transformed values. There is, as you can expect, a relationship between the arithmetic mean of these measurements and the geometric mean of the measurements and the geometric standard deviation of the measurements. So the formula mu of x is mu of g times the exponent of, and within parentheses, 1/2 the square of the log of the sigma g, or geometric standard deviation. And what this tells us is one very important thing, which is the exponential factor is always going to be greater than 1 because sigmas of g, the geometric standard deviation, is always going to be greater than 1. And so since the exponential term is greater than 1, the geometric mean, sigma g, multiplied by a number that is greater than 1, is the product is always going to be greater than the geometric mean by itself. What this implies is that the arithmetic mean is always greater than the geometric mean, as long as the geometric standard deviation is greater than 1. And that's a very important feature of log normal distributions, that the geometric mean is less than the arithmetic mean, or the arithmetic mean is greater than the geometric mean. So it's a skewed distribution which leads to this feature. And in a similar fashion, there is a relationship between the arithmetic mean, geometric mean, and the standard deviation. And the formula is given as shown here. So sigma g is the geometric standard deviation, and it's the exponent of the square root of the log of 1 plus sigma x squared divided by mu x squared, and where sigma x is the standard deviation and mu x is the arithmetic mean of the values. So as we can see, the sigma x divided by mu's of x is the coefficient of variance, which means the relative standard deviation, or the standard deviation divided by the mean, and you take the square of this ratio and you add 1 to it, and then you take the logarithm of it, you take the square root of it and exponentiate it. And so the geometric standard deviation, again, is a quantity that is going to be greater than or equal to 1. So let's quickly review what we know about normal distribution, because it is going to help us understand the log normal distribution. So a normal distribution, as we all know, is a symmetric distribution. It is this bell-shaped curve. It is also known as a Gaussian distribution. And as you can see in this graph, the peak of this distribution is centered on the mean, mu, or the arithmetic mean, but this is also the median, which means that it splits the distribution into 2 equal halves. So 50% of the distribution is less than mu, 50% is greater than mu. And mu is also the mode, meaning the most frequently observed value. And this is one of the key features of a normal distribution, that the mean, the median, and the mode are the same quantity, mu. The next important feature to remember is that if you consider an area under the curve within one standard deviation in the plus and minus directions. So if you look at the area under the curve between mu minus sigma to mu plus sigma, that is 68% of the total area under the normal distribution curve. And that is shown in the table below this, where if you look at z equal to 1, so z is the coefficient in front of the sigma. So we can think of it as mu minus 1 sigma, where z equal to 1, to mu plus z sigma, where z equal to 1. And so the probability in that table, as you can see, is 68%. The other important numbers on this are when z equal to 1.645, which means that if you go between mu minus 1.645 times sigma to mu plus 1.645 times sigma, the area under the curve is 90% of the entire area under the distribution. And one last important number that we need to just keep at the top of our head in our memory is z equal to 1.96. So mu minus 1.96 sigma to mu plus 1.96 sigma contains an area of 95% of the total area under the curve. So these are some important statistics that we need to remember about the normal distribution, because they are quite handy when we come to thinking about log normal distributions. What this slide shows is a typical log normal distribution curve. And as you can see, We have some parameter x on the x-axis, and the y-axis is the probability density function. And unlike the previous slide, now we have a skewed shape to the curve. And in this particular example, the geometric mean of this distribution is 10, and the geometric standard deviation is 2.3, as shown in the upper right-hand side of the graph. So you can see that the geometric mean of 10 is not near the peak of the distribution. That is the mode. And so the mode, which is the peak of the distribution, is in fact somewhere around 5. And so the mode is less than the geometric mean of the distribution. The other important thing that is shown here is if you look at the extreme left-hand side vertical bar here, and that is marked as mu g divided by sigma g raised to the power 1.6. So it is sigma g that is raised to the power 1.6, not the whole ratio. Okay, so mu g divided by sigma raised to the power 1.96, that is 2.2. And on the right-hand side, you see another very small vertical bar, mu g times sigma g raised to the power 1.96, and that comes out to around 45. And so the total area between these two vertical bars is 95% of the total area under the log normal distribution. And we'll talk about how this occurs in a bit. So in this slide, we'll continue our discussion of the log normal distribution. Just like in the case of the normal distribution, the table shows the z statistics for the log normal distribution. But there is one important difference, which is that in the normal distribution, we would say, for example, that the area under the curve in mu minus sigma to mu plus sigma is 68%. Except now we are looking at a log normal distribution. And in the case of a normal distribution, we would say, for example, that the area under a normal curve between mu minus 1 sigma to mu plus 1 sigma is 68%. In a log normal distribution, this changes because now we are talking about the logarithms of the quantity. And so we would say that the area under the curve between mu g divided by sigma g raised to the power sigma to mu g times sigma g raised to the power sigma is 68%. Here, in this case, z would be again 1. Likewise, for z equal to 1.645, we would say that mu g divided by sigma g raised to the power 1.645 to mu g times sigma g raised to the power 1.645 is 90% or 0.9. Now we are talking, in fact, about the ratio or the product of mu g times sigma g raised to some power of z. So if z were equal to 1, then mu g divided by sigma g raised to the power 1 is in fact the 16th percentile. And mu g times sigma g is in fact the 84th percentile because the distance between the 16th and 84th percentile is 68%. And that's how we can understand the log normal distribution. So another important result of this is that the geometric standard deviation can be simply thought of as the ratio of the 84th percentile to the 50th percentile. In the case of a normal distribution, we would say that the standard deviation is the difference between the 84th and the 50th percentile, but here we are talking about the ratio of the 84th to the 50th percentile. One other important phenomenon here to remember is that the sigma g, the geometric standard deviation, can never be less than 1. And there is a very simple reason for this. If, let's say, sigma g equal to 1, that basically means that all the values in the distribution have the exact same numerical value. So all the percentiles have the same numerical value. And if sigma g were less than 1, then we would have the absurd result like a lower percentile, meaning let's say the 16th percentile is in fact greater than the 17th percentile, which of course doesn't make any sense. So in order for the percentiles to follow what we expect of percentiles, meaning the higher the percentile, the greater the value, we need to have the geometric standard deviation be at least 1. So now let's move on to the next slide. And here we want to look at the effect of the geometric standard deviation on how skewed a particular log normal distribution is. As I said just in the previous slide, a geometric standard deviation cannot take a value less than 1. It at least has to be equal to 1. And so in this graph, I'm showing several log normal distributions, all of which have the same arithmetic mean. Notice that I said arithmetic mean, not geometric mean. And the value of the arithmetic mean is equal to 1. Now let's look at first the curve corresponding to a geometric standard deviation of 1.2. So this is it looks almost like a normal distribution. It looks very symmetrical, and as you can see, the mode of this distribution is very close to 1, which is characteristic of a symmetrical normal distribution. And in fact, the geometric mean is also going to be close to 1. And if you look at the tails of the distribution, you can see that it falls off very rapidly, and by around on the x-axis, if you see about 1.8-ish, it goes down to almost 0. Now, if you consider a slightly higher geometric standard deviation, so let's look at the curve corresponding to GST equal to 2.0, you can see that the peak is no longer at 1, it's around 0.5. And the arithmetic mean has not changed, but the peak of the curve has shifted to the left. So that's one thing, okay? So if you were to calculate the geometric mean, that is also going to be much less than 1, but probably greater than 0.5. So it's somewhere in the middle between the mode and the arithmetic mean. If you now look at a geometric standard deviation of 4, you can see that it is now very skewed, and the peak is around almost 0.1. So that's the mode of the distribution, and the geometric mean will be somewhere between that and the arithmetic mean, which is still at 1. The other important thing to remember is that if you look at the tails of the distribution at the extreme right side, the curve corresponding to a GST of 1.2 falls off very rapidly. Whereas if you look at the curves for GST equal to 2 or 4, they are not falling off as quickly. This means that there is more probability in the tails of distributions with higher values of GST than in distributions with lower values of GST. What is the importance of this for exposure assessment? So let's say we have a similar exposure group whose exposures are described by a distribution with a GST of 1.2. So their distribution looks almost like a normal distribution, and the exposures of the workers in that SCG are going to be very in a tight range, somewhere between 0.5 to 1.5, 1.6. And it's very unlikely that you will find large values greater than 2, for example. But if you have an SEG with a larger value of the geometric standard deviation, a GST of 2 or 4, then it's more likely that you will find large exposure values. So there is a greater likelihood for observing larger exposure values. And why does this matter to us? It's because, as I said in the beginning of these lectures, we in industrial hygiene make very few measurements. And so if you had to make, let's say, a small number of measurements, somewhere 3 to 5 measurements, then just probabilistically speaking, we are more likely to observe those measurements in the lower end of the curve where most of the probability is accumulated, near the peak of the curve. And so on the basis of those smaller values, we want to understand the full distribution of exposures extending into the much larger values. And that is always more challenging than if you had a tight range of exposures. The goal is to predict the upper tail of the exposures based on a few values that, because of the nature of this skewed distribution, we are observing at the lower end of the distribution.